Ready? Okay, we're going to finish up a lecture here. I talked about development length. I'm not sure how this is going to run exactly on Canvas. We're going to fill in the blanks as we need them. But lecture is on chapter 15 of your text. Chapter 15 is concrete columns and frames. We're going to deal with concrete columns. The chapter is set up so that it is driven by tables. So we're going to look at 3 types of columns. They're all concrete, of course. The 3 types are the shapes. We're going to deal with a square. We're going to deal with a rectangle. And we're going to deal with a round column. Okay. Hopefully everybody knows the difference between a column and a beam. A column is a vertical member that typically has beams and girders framed into it that ultimately rests on top of a foundation, typically a pedestal or something, and then moves down into the footer. The footer transfers the load from the structure into the soil, and the soil, so if it's got the right soil bearing capacity, ends up holding the structure up safely. Okay, our columns are typically in compression, the ones we're going to deal with. Okay, so I got a column, whatever shape it is, doesn't matter. I'm going to draw it round. Round seems to be something I can explain better. I've got a round column. I'm going to put a load on it, and I'm going to try to squash it. Okay, now I am on page 493 if you've got your text handy. And I'm going to try to explain how the interaction between concrete and rebar work. Okay, so I've got a load. I'm going to put it on the column. And the column has rebar in it. The rebar is used in compression. Why do we use rebar? So that we can limit the size of the column. Steel has a tremendously larger modulus elasticity. It's about 10 times that of concrete. Therefore, I need a lot less steel to carry the load than I would concrete. So the combination of the two work together. It's also nice to have a non-brittle or a ductile material buried inside of a brittle material. The brittle material just kind of explodes, where the ductile material has a elastic range that allows it to stretch a little bit before it breaks. So it's nice to have the combination of the two. So when we push on it, as you look at page 470, you can see the 3 things that can happen. Okay, one is it can just squash the living snot out of it. Okay, so I can actually push it so that it compresses and it just has a cross section that can't endure the compression. So that is typically a combination of both. The concrete and the steel take the load. The next picture shows it like a marshmallow. Marshmallow, you push on it from the top. The marshmallow gets fatter and shorter. It pushes out. It turns into a curve-shaped object. And that particular shape then has 2 components. It has a component that's associated with concrete and steel, and it's a lateral movement. So I'm trying to keep it from pushing out. And of course, the steel holds it together. And then the last one is shear. Those of you who have been in the materials lab and put a concrete cylinder in a compression test probably didn't realize what was happening, but your specimen probably failed under this condition, which is shear. And shear means the corners of the concrete going to push hard enough that it actually pushes the corners off. And then the area keeps getting smaller. As the area gets smaller, the stress gets bigger, and then it'll just basically crumble. So this is a function of concrete and steel. I'm going to take up the load. The steel tends to hold the thing from ballooning out, turning into a marshmallow that's being flattened. And this, of course, shear has two. And if you look at it, okay, the steel here, I'm talking about both components, the vertical and the horizontal. So the bars are going to be vertical, but it's also going to have a cage that goes around it that we tie the bars to so they stay in position. That cage acts as a tying device, and also it takes out the horizontal loads or thrust. So here, since we've got a vertical and a horizontal and our force is on an angle, part of the force is taken out by the vertical, part by the horizontal. So, and it does have some shear value, the concrete. So the concrete takes care of part of this force, and the steel aids it and adds a horizontal and vertical component to take out the 45-degree angle shear force. So we're trying to, the two, what I'm trying to get to here is that the two in concert end up giving the concrete column its strength. So it's a combination of concrete and bars. They show you a bunch of bar configurations, and on each of them, they will show you the cage. The cage is the bars that go around that we tie to. So in a square, we will have rebars that are in typically a square pattern. They can be infilled, there can be some inside. So if you look on page 497, they show you. And we make those just like we do stirrups almost identical. The bar goes right around. It's a littler bar, 3 and 4 typically. We bend it into a square, and then we take and put the square around the bars and take wire and wire the bars in place. So when we pour the concrete, they don't move, and we can pick it up with a machine, a JLG or a cherry picker, and we can pick it up and drop it into the formwork. Secure it, pour the concrete, and then we've got our cage in there with bars, and the cover will be maintained by spacing. So this, if you looked at it from the side, would look like this. There's my cage, and there's the horizontal ties. Okay, and it shows you there, it says primary forms of column reinforcement, rectangular layout of vertical bars with lateral ties. Then they got a circular one right next to it. So rectangles and squares are basically the same. I have seen square cages dropped into round sonotube forms for round columns. Reason being is that it's cheaper. But the preferred way is to have your bars go around in a circle, and then have a circle go around them. And that circle is typically a helix. So it's a bar like a corkscrew. Just like a corkscrew, it screws itself right up around. And then, of course, we tie the bars to the corkscrew. You can see common sense tells you it's a lot cheaper to take this and bend a square rather than this. Try to make a helix, which you got to roll it around something and make it a nice circle so that the bars are spaced properly. So page 497 gives you that. Okay, that's basically it. Concrete cover, if you look at it on page 499, minimum 1.5 inches is needed when the column surface is not exposed to weather and not in contact with ground. So if you've got a column inside of a building, something like that, 1.5 inch cover works. If you got a column that's outside but it's not touching the ground, it's above ground, you need 2 inches. And then when you put it underground, you need 3. Makes sense. What does cover do? Cover gives us a barrier between the weather and the bar. And as long as we have that barrier, then the bar doesn't get wet, dry, which causes it to rust. When it rusts, it expands. When it expands, it explodes the concrete. And we end up with bars that are showing and the concrete is blown off of the face of the column. And that's something we don't want to deal with. So there's your cover right above it, says ties. They use number 3s for bars that are 10 and smaller, and number 4s for 11 and bigger. So this guy right here is going to be a number 3, or a number 4, like I said a few minutes ago. And depending on the size of the bars it's holding, if they're 10s, these are 10s or smaller, we'll be using the number 3. If they're bigger than that, we use the number 4. Okay, this is general information basically, give you an idea. The chapter isn't centered around that. It's centered around tables. If you go to page 501, you see a bunch of layouts. It shows you what could be and what you could see on drawings when you get in the field. Okay, then you go back and it shows you about forms. Hopefully you know that we make this out of plywood, okay? We make a form out of plywood and then sand it up and plumb it and then fill it and then drop the cage in and then we fill it with concrete. Okay, this guy, it's a bear to bend the plywood, so we have something called a sonotube. So we buy those in different diameters. Sono tube. Basically, if you something you deal with quite frequently, you get to the end of the toilet paper roll, that's what's left, a sonotube, okay? So it's a spiral, it's made out of cardboard, it's got a covering on it so the concrete doesn't adhere to it. We stand it up, plumb it, drop our cage in, pour it, then strip it. So that's the basic information associated with columns. Okay, now for what you have to worry about. You have to worry about being able to use the tables. Okay, so I'm going to redraw those pictures, and underneath them I'm going to give you the tables you need. So I've got a square, I've got a rectangle, and the rectangle sometimes is noted as being an oblong column. Morning. An oblong column, okay? So it's a rectangle. And the last one is a circle or a round column. So you've got tables. Here you've got 4 of them. Here you've got 2 of them. And here you've got 1 of them. Let me shut us off for a minute. Well, you want to come in and